I think Nima puts the talks on YouTube, so if you're fine
Yeah.
with that.
It's okay.
All right. So today we have Pawel Kaputa from University of Warsaw. He'll be giving a talk on quantum complexity and the Krylov basis. Please.
Okay, so thank you, Troy, and thank you everyone for inviting me and giving me the opportunity to speak about his recent works. Okay, you can see my screen changing.
Yes, we can.
Okay, good. So outline of my talk is as follows. I'll give a brief introduction and motivation, mostly based on kind of holography. And then I'll discuss more technical parts that are not so holography related, but I think kind of broadly interesting for both holography and quantum information or quantum computation community. So this will be this middle part, and I'll talk about the Krylov basis and the definition of the spread complexity of states. And then I will give examples and I will conclude and pose some open question at the end. And this will be based on two papers that we wrote this year with Vijay Balasubramanian, Javier Magan, and Qingye Wu from all of them from the University of Pennsylvania, and also earlier this year with Javier and my student Dimitrios from Warsaw. And basically, please stop me at any point if you have some questions or comments, want me to explain something in more details. I'll be very happy to discuss. I prepared various examples, but if I don't go through all of them, that's also fine. So hope it's going to be interactive. So yeah, the introduction and motivation is as follows. Maybe a kind of brief review of the context. I'm sure you're kind of more or less familiar with this recent entanglement or quantum information revolution in ADS-CFT. And all these developments certainly changed our perspective on holography itself and also on quantum black holes. And they even led to a new paradigm that somehow holographic geometry might be emergent from quantum entanglement. And this has been supported by many famous examples in the literature, but somehow the success of all this program has been heavily relying or has been mostly due to very useful tools from quantum information like entanglement entropies or the Renyi generalizations, and also some related definitions of that we could use, and somehow they were all defined in a very precise and sharp manner. For example, using some replica tricks and powers of density matrices and this sort that we could then somehow directly import from quantum information to quantum field theories and ADS-CFT. But recently, there are more demands for fine-grained or late-time probes of ADS-CFT and these holographic geometries, and they go under the name of complexity. I'm going to be a bit more precise what we might mean by this complexity, but here I'm just putting it in these quotation marks. And in this talk, I'll try to discuss whether there's, or try to entertain one possible direction for a universal definition of this thing that we call complexity in this talk. But before I go there, I want to, maybe not, if not everyone is familiar with how this all started, maybe I'll give you a brief introduction to why we actually want or need complexity in ADS-CFT. And this is going to be a bit pedagogical or broad, so I'm sorry if this is too slow or too basic, but maybe for people that are not familiar, this might serve as a nice starting step for what's going to follow. Some basically historical motivation. Okay, so somehow the need for complexity, for quantum complexity in the context of holography started or can be dated to this paper of Hartmann and Maldacena from 2013, when they actually considered this thermophile double state that, due to earlier works of Maldacena, is conjectured to be dual to the thermophile double, dual to the maximally extended two-sided black hole in ADS. What Hartman and Maldesana did, they consider the time evolution. So the non-trivial time evolution of the state is done by either one of the Hamiltonians. So in this thermophile double state, we consider this maximally entangled copy, two copies of a CFT, but it can be actually any quantum system. And we put this in this entangled state, which is basically a purification of the thermal state. So the Z of beta is the thermal partition function at inverse temperature beta. And basically what they consider is this time evolution with one of the Hamiltonians, so either with the left copy or with the right one or the sum, and that gives you this non-trivial evolution. And they actually consider the evolution of entanglement entropy in this setup. So here I'm plotting the result from their paper, where they consider some two intervals, interval A and B. Let's say they are the same in one in each of these copies. And they notice that entanglement entropy, as in many of the similar quench processes, evolves with time, but then after some time of order, the size of the interval that I chose, like L here, it saturates. On the other hand, the dual geometry, this evolution that corresponds to this particular state, can be regarded as evolution along these slices that actually go from one side to the other through the wormhole, so through this Einstein-Rosen bridge that connects those two asymptotically ADS space times in this geometry. And somehow these Einstein-Rosen bridges, they continue to grow with time, even past this entanglement saturation. So Lenny noticed that this is actually maybe a puzzle or an obstacle to this entanglement from geometry program, because simply entanglement entropy might not be enough to tell us all the information, especially for late times, about this dual geometry. And then he proposed that, well, he asked this interesting question: what is the CFT dual of this growth of Einstein-Rosen bridges? And then he tried to give an answer that there should be some notion of complexity, maybe related to circuit complexity, but it was not very specified, of this time-evolved thermophile double state that then in CFT could capture this growth of Einstein-Rosen bridges for the late times. So this was one of the first encounters when we started thinking about these notions of complexity for very late time physics of this state and this geometry.
Quick question, Pawel.
Hi, Nima. Yes,
Hi.
please.
Sorry for being late. I was a few minutes late. I was in a meeting. So it's a very basic question, something that I've been confused about. So the left and right argument, so there's a geometry argument and then there's quantum mechanics argument. The quantum mechanics argument sort of assumes a finite dimensional Hilbert space. So if your entropes, entanglement entropies are divergent, they could continue to grow forever, right? So the right picture doesn't quite directly correspond to the left picture, right?
Yes, I think that's right.
But I mean, then how do we, I mean, is there, so this is more than just a mathematical observation. When something is divergent, it can grow forever, right? So what's the sharp, is there a sharp way of expressing this that's in terms of finite quantities, or?
You mean some renormalized entropies or something like that?
Some mutual information, something of that nature.
Yeah, that's a good point. To my knowledge, I don't, I mean, short answer is that I don't know. Like all these arguments were mostly for the entanglement entropy. I think that, I mean, indirectly, that might be also related to this proper way of defining this growth for late times, whether you use a good quantity and so on.
It's just that I just very naively, I would have thought that it should not, just by examples of infinite sequence of qubits, it should not be very difficult to rate for setups where entanglement entropy continues to grow forever because it's just divergent.
Right.
But anyway,
well, yeah, you know, I think the issue of cutoff is very important. And I think one needs to, once we will come up with some proper quantities to probe all these issues of complexity, I think we need to address this cutoff, maybe even more severe. Because in some sense, in entanglement, we kind of know what to do with the cutoff, and we accept to live with it, right? When we are interested in some area like leading divergences and so on for matching with holography. But I think maybe with complexity, I think there will definitely be some deeper story with the cutoff. In some sense, I sympathize with you. Of course, we can always like put any field theory on some lattice, right, and work with finite cutoff. But then you need to be precise. What do you mean by this long times and so on?
Exactly.
Also in terms of the cutoff.
Exactly. Precisely. Thank you so much.
Okay, so here is just maybe kind of I'm going through some history a little bit. And then also there was a second part of this story of complexity, and namely this word or this buzzword complexity came up in the story of operator growth or out of time order correlators and also operator size. And this can also be dated back to this earlier works by Schenker and Stanford and collaborators, where they studied also some small perturbations of thermophile double state. And then they wanted to see what kind of effect it can have for the entanglement in the thermophile double state. And this was even in their paper dubbed as the butterfly effect. So they inserted some light local operator at some early time on one side of this thermophile double state, and they noticed that, for example, if the T is chosen sufficiently large, then it can destroy this fragile structure of entanglement, even though the operator OL can be chosen to be very light. And then it somehow evolved into this story of precursors, where we studied some operator W, some general operator in CFT with some unitary evolution. And the goal in this program, somehow this discussion on the butterfly effect and this operator growth matured into some precise questions. How do we, whether we can define some universal working definition of the operator size in many-body quantum systems or in quantum field theories, or something like an operator complexity. And finally, whether these notions could be somehow related to the quantum chaos, like whether this growth of operators can be linked directly to the quantum chaos and so on. And this, I think this has been kind of in many ways, this was kind of parallel, but not so much intersecting with this earlier Lenny kind of notions of complexity. And some partial answers were given, namely in terms of out of time order correlators. We learned that there might be very important probes of the quantum chaotic natures of, let's say, some holographic CFTs, but still, I think this this kind of second field where we talk about more operators than state is still actively developing, and still these notions of operator complexity are very important there, and we are also trying to find what this complexity might mean there. Okay. So these are the two things, and basically, given these two early motivations, there has been many attempts and hopes for what this complexity could mean and what this complexity could give us. And one can, I'm just giving a very brief division here, but one can put them into roughly two groups. So one could be these notions of complexity for states, and that would mean in terms of maybe complexity language, we would be interested in some complexity of formation of a given state. So let's say we start from some reference state, we want to go to some target state by some operations, and we would like to understand how difficult that is. And also for states, we could be interested in evolution, let's say, of some particular, say, scrambling Hamiltonian or simple integrable Hamiltonian. How can we quantify it? And there has been various approaches. So famous one by due Nielsen and collaborators was kind of being generalized into more holographic context. Also, there was more like a approach based on Euclidean path integrals. But basically, it is clear from this work that we need some good distance measure. So maybe like a quantum information metric or something of this type that will be able to distinguish between states for late times. So maybe relative entropy of the sort that we can use as a very good probe for all these processes. And the hope is that once we understand such a nice measure, then it will somehow tell us something about the growth of this Einstein-Rosen bridge or the late time physics of black holes, or maybe something about singularity. But we're nowhere there yet. And on the other hand, when we talk about some operator complexity, we would like to understand what is the universal way of quantifying the growth of operators, maybe this quantum chaos. How can we probe it by some notions of the growth or the size or complexity of operator? And again, some progress has been done nicely in the context of the SYK model, where some number like operator can be used to quantify the size of operators in there. There has been some story about some momentum and the relation of momentum of a particle that falls into ADS2 and some growth of the operators in maybe also kind of SYK motivated models, and also out of time order correlators that are mostly linked to this chaos, but also the relations are not like, they're still kind of open between the one and the other. And the hope there is somehow slightly different, that once we understand this good notion of the operator growth, then this will be related to the near horizon or maybe behind horizon physics of black holes in a similar way. Like, for example, when you think about out of time order correlator, in the bulk is some process of scattering happening close to the vicinity of the black hole, then somehow this operator complexity notions, they would be related to this physics, but also the relation between 1 and 2 are still not clear. And this is kind of historical overview, and also tells us a little bit, I want to tell you a little bit where we stand more or less from my modest perspective.
Can I ask a little bit of a weird question about this? The original argument that you presented, or the argument by Lenny, was saying that, well, it seems like time goes on for an exponential amount of time, for a very, very long time in holography, but we expect entropy to thermalize really fast, to equilibrate very fast, right? But this is just bipartite entanglement, right? Which is just one number you would associate to your bipartitioning of your multipartite state. Why did we need to invent a new concept? Why didn't we call complexity a multipartite entanglement measure?
Yeah, I think that would be fair, and somehow that's what we are trying to understand better, right? Like whether how much of this quantum information do we really need? If we need some good, like as I said, some distance measures, like maybe relative entropies or maybe multipartite relative entropies that we can probe in the bulk, then it's fine, and we can stop there. But also, I think the point is also that we need some, of course, there's also some times for which the bulk argument will be valid, right? After some time, we cannot. So we cannot use the semi-classical or classical bulk and so on. And also when we talk about multipartite entanglement, of course, we need to also specify to which order in 1/n we are working and so on, right?
Just naively, I'm thinking that the bulk theory holds until for e to the power of s, or power law in S, right? And entropy saturates in some lower power of S, but you could construct multipartite entanglement measure, hopefully. I mean, it's a little bit of a difficult theory to build, but anyway, thank you.
No, I mean, I think these are good questions that once you start thinking about this, you usually have you want to be more modest and just kind of go minimal beyond this story and take this as arguments. But I think once you start thinking a bit more about these operators and so on, maybe then you start thinking that indeed something like the size or operator complexity would be more useful, and maybe it's not immediately obvious how you could just generalize this in terms of multipartite entanglement, but I'm not saying it's not possible. Okay, so thanks for questions, and please, I'll be very happy to also hear your opinions and comments at any point. So that's also very valuable for me. So stop me with any kinds of questions. Okay, so in the rest of my talk, I'm going to be talking about some proposals or recent developments that allow to think about some framework for complexity, maybe in the not directly in the context of holography yet, but somehow in the context of many-body systems or in the context of quantum field theories, where we could apply to these two problems that we have. This, for example, evolution of states or the state type of complexity, as well as the operator growth and complexity of operators. So somehow this is what I'm gonna talk about, and this is what I've been excited for some time. And in the remaining, I'll discuss the notions of complexity based on the so-called Krylov basis that can be universally defined and computed in systems from quantum mechanics to quantum field theory. And I will then discuss some recent results for both states and the operators as I gave in the motivation. Actually, this is mostly based on this paper with Vijay and Javier and Jingyu from this year, but actually there has been many excellent references already on using these ideas for the growth of operators that I list here, and that I will not, maybe I'll mention only some of them, but this list is here and it's also kind of actively developing. So I'll be mostly focusing on states, but please have this in mind. And maybe if you're already familiar with these notions of Krylov complexity of the operator growth that you see in these references, then maybe it will also be easier to follow. Okay, so let me start with maybe very concrete and basic definitions. You can now forget about all these historical and maybe political motivations, and let's go to very concrete ways of trying to define this these tools and building blocks of what we might be calling complexity. Okay, so let's say we're interested in some unitary evolution, or you might as well think about this as some quantum circuit that I denote as some psi of t, where we start from some initial state psi 0 and we apply some unitary e to the minus iht. This is a very general setup, as you can see. It can be applied. You can think about this h as being your physical Hamiltonian, or being a circuit Hamiltonian, or even being some modular Hamiltonian, and so on. And t can be your physical time or some circuit time. This basically framework will work equally well. And the point is that once we start from such a circuit, we can formally expand the state in the powers of time t. And then the states that appear on the right of these expansions, they can be written as this psi n, which are basically different powers of this Hamiltonian h applied to this initial state psi 0. So we have basically this subset of psi 0 h and all the powers of h to the n applied on this initial state. And the goal is that given this subspace, this subspace is called the Krylov subspace. Maybe this is something that you might have heard in your early algebra, where you start with some basic vector and you take some matrix and you apply all the powers of that to generate the so-called Krylov subspace. And then based on that subspace, we would like to construct an orthonormal basis. This is this Kn that I will be calling Krylov basis. And this basis is done usually by the so-called Lanczos algorithm, but you can just think about it by taking this Krylov subspace, so basically this psi 0 and all the powers, and step by step recursively construct the basis using Gram-Schmidt orthogonalization. So as you can see, this is done recursively by starting with some state n+1, and then on this we start with the Krylov basis vector Kn, apply the Hamiltonian h, we subtract some coefficient an, and also subtract the basis vector Kn-1 with some coefficient Bn, and then we normalize. We define Kn by basically this vector an normalized by Bn to the -1. And in this algorithm that we do step by step, these coefficients an and bn, they are the so-called Lanczos coefficients, and these ans are basically the expectation values of h in this Krylov basis vector Kn, and bn is just the norm of this vector an. So basically we can just choose them by doing this procedure. What we get step by step is just some number of orthonormal basis vectors, but also we get this by this Lanczos algorithm, we get these Lanczos coefficients for any n. And I'll be choosing, because we can always like rotate these vectors and normalize them such that these bn's are chosen positive and real, and also an's are going to be some real coefficients. And then also the algorithm, the way I wrote to you this algorithm, it works such that it makes sense when we choose this b0 equals to 0, and of course this Krylov basis vector k0 is just this initial state psi0. It should not be anything abstract if you, of course, know your Gram-Schmidt orthogonalization, and it's kind of good to do it step by step, for n equals to 0, 1, 2, you will see that it works as you would expect. So that's how you basically, from this nth powers of the Hamiltonian, you generate the basis. And once you have done that, okay, so one more step, actually, by definition of this algorithm, this algorithm it constructs a basis in which this Hamiltonian that you started with becomes tri-diagonal. So as you can see here, this an plus 1 is nothing but just some bn plus 1 times the original Krylov basis vectors, and you see that from this, if you reshuffle these elements, you can see that this Hamiltonian, when it acts on Krylov basis vector kn, it generates 3 terms. So that's what I mean by tri-diagonal. Here, when we act with the Hamiltonian on basis vector an, we have this linear, we have this diagonal piece with Krylov basis vector kn with coefficient an, and then this 2 off diagonal bn plus 1, bn with kn minus 1. So if you write this in this Krylov basis, this is how your Hamiltonian looks like after this procedure. And this is the so-called Hessenberg form that actually, once I give you any matrix, for example, some finite dimensional matrix, you can always put it into this form using some very good packages in Python or Mathematica. And this will be important in kind of more technical applications later. Okay, so this is the so-called Krylov basis. And basically, now we expand our state that I started with. So this is this psi of t e to the minus ht psi 0 in this Krylov basis. And the coefficients in this basis, I will denote as this phi n of t. Okay. And by definitions, these coefficients by unitarity, these coefficients their absolute values, they sum up to 1. So we can associate probabilities Pn with this phi n of t. And also by this definition of the Hamiltonian, how it acts on this Krylov basis vectors and the definition of states, you can actually derive this discrete Schrödinger equation for these coefficients. So if you basically take this state and heat it with I delta t, you will see, and then reshuffle the elements on the right according to this action of the Hamiltonian. You see that this amplitudes, the coefficients in the Krylov basis of your given state, they satisfy this discrete Schrödinger equation as I write here in the box here, with the initial condition that these coefficients at t equal to 0, they should project on this initial state k0 or psi 0. So this is the condition that you have, and this gives you the complete information about the state psi of t in this Krylov basis. Okay. Good. So is this clear? Yes. Yes,
so
please.
The fact that this is tri-diagonal says that if you take some state kn, right, and act with, I guess, and compared with, I want to say kn plus 2, they're orthogonal, right? They're completely orthogonal.
Yes.
But by acting with Hamiltonian, you can go from one to the other, right? So you act with the Hamiltonian, and Hamiltonian is a local operator. I'm just wondering are we saying that we have 2 orthogonal states of many-body quantum systems, for instance, right? And then you act with Hamiltonian, which is a local operator, and you go from one to the other?
Well, no, it's not exactly that. Like we take, okay, there is a state that has, let's say, certain power, let's say 2 powers of the Hamiltonian in it. And then but it's not the full state. We need to orthogon, we need to add some other parts from this algorithm before, and then we can take another state with, say, 4 powers of the Hamiltonian in it. And then you in this procedure of computing that state K4 with 4 powers of the Hamiltonian, you also subtract everything else such that basically these two are orthogonal. But it's not like you simply go from one to the other by application of the Hamiltonian.
But everything that you subtract and add, these are local operators, right?
Yes.
No, but you get the same state plus a little bit of the orthogonal. It's not that you should get the orthogonal.
Okay, but what I'm saying is that you can with the part that you subtract could also be found as a local operator acting on this guy. And anyway, I guess I'm just gonna say, let me give an example, and we can come back to this maybe at the end of this talk. Let's say you create your state by acting on the vacuum with some operator O, right?
Yes.
Then you're gonna say that with combination of the second derivative and third derivative and the first derivative time derivatives of O, you're going to construct a vector that is orthogonal to the first one. Is that correct? Where O is the local operator. So then it looks like it's just a local operator that we're multiplying it to go from one to the other. But anyway, we can come back.
The Hamiltonian is the integral of local, no?
Yeah, but I still call that local operator. It surprises me that an integral of a local operator is, yeah, anyway, okay, thank you.
Maybe it will be clear in the next slide. So how this non-locality could work. So basically, let me just say this one more time. So this is this algorithm, and what is very important in this algorithm. So is exactly this, is this recursive procedure, and in this recursive procedure we have to use these coefficients ANs and BNs, these Lanczos coefficients that play a very important role. And basically, they enter directly into the Schrödinger equation. So once we know these coefficients AN and BN from some procedure of doing it for some initial state, and then some Hamiltonian H, so then we can basically solve this Schrödinger equation, and that will be all the information that we will know about this process. But keep in mind that this process depends on 2 things. It depends on this initial state psi0 and on this H here. So once we know those 2, then we can go through this Lanczos algorithm to find ANs and BNs and this expansion. Okay. So, but psi0 and H, this is some initial data that you tell me that this is the process that works. Okay. So, and let me also point that basically these Lanczos coefficients that enter directly into this most important equation, they can be also read off, or they are encoded in the so-called return amplitude. Maybe for many people, this is usually called autocorrelator, or sometimes also log-Schmidt amplitude, in the sense that the square of this return amplitude is something called log-Schmidt echo. And this return amplitude is defined as basically taking the state at t equal to 0. So this is our psi0, and then projecting projecting the state psi of t on the initial state. So this is how I'll define it in most of the talk. I will also mention some slightly different convention that uses basically a star of this instead of what I'm writing here. And this is just an expectation value of e to the iht in this initial vector psi0, or by construction of this Krylov basis. This is this Krylov basis 0 star. So basically psi0, as I wrote here, this is how it is expanded, and k0 is basically psi0. So if I project it on psi0, I'm just keeping this psi0 of t. So this psi0 actually has all the information about ANs and BNs by construction. And how do we get it? So we can compute moments of this return amplitude. So if you just compute n derivative of s of t at t equal to 0, this is of course by definition just the expectation value of I h to the n in this initial state. Then you can run again some particular algorithm that is very well defined, but I will not show you all the details here, that tells you like how do you relate these A's and B's to the moments. So for example, well, if you're really interested, there's like some computer science algorithm where you can basically draw at the very bottom of this graph here all the moments mu n, and then by counting appropriate paths from the initial point to this particular moment and multiplying the weights, that tells you what's the relation between the nth moment and then the previous power Lanczos coefficients A's and B's. So for example, this A0 coefficient is just related to the expectation value of H. And also the second moment is related to the sum of two paths. So to this moment 2, you can go by basically this path that has the weight of minus A0 square, or you can go by this path that has the weight of minus B1 square, but there's no other path. So that's how you compute it. Let me actually point that there's actually, it's nice to look at the inverse relations. So of course, trivially A0 is just the first moment of whatever your H here is, the circuit Hamiltonian, but B1 square is, for example, the difference between the first moment square minus the second moment. And so it's actually, it's very interesting to also, given this general definition, it's interesting to think what is the physics of these ANs and BNs in general. And this has also been explored a bit by Vijay and Javier, but what we are
sorry, maybe you say, but what is the state size 0? Is some random state?
You can choose it to be anything. Of course, you know, in most of the applications, you want it to have some non-trivial evolution under this e to the minus IHT, but up to what I have presented here, it can be any state.
In the Lanczos procedure, usually is to choose a random state, but in physics, here, I don't know if you are interested in
I will show you some particular examples, but the procedure, of course, works for any state. Of course, the interesting thing will be to take some non-eigenstate of the Hamiltonian or some random state, as you say, and see how the evolution goes, like, you know, to study the properties of this Hamiltonian H when it does this evolution. But if you were, you know, if you just not randomly, but if you chose a particular state and wanted to run this procedure, it will also work out. But maybe these Lanczos coefficients, there will be like only very small amount of them, and the process will stop after only a few steps because you will not need more states. You will not generate more states, more orthogonal state, but by just applying this Hamiltonian to this very simple state that you started with.
Okay, thank you.
Thanks. Okay, but I wanted to comment that actually the physics might be also interesting from the perspective of entanglement. So we can take this H to be just modular Hamiltonian, and then you can see that A0 is directly related to the expectation value of H in this initial state, which is nothing but entanglement entropy. And for example, B1 square is something that we call capacity of entanglement. And you can go like higher steps in terms of A's and B's, and they kind of extract higher entanglement type information from the state in this particular ordered manner. So this is also something we are thinking about for future applications of this idea of Krylov. Okay. And then maybe just to make a quick connection to the previous work. So all these works that that brought this Krylov story into attention of many body and holography, they were interested in the Heisenberg evolution of the operator. So there we.
Sorry, Pawel, can I ask you a question from the last slide? I'm so sorry. So the comment that you made at the end seems very intriguing. So here you're going to take, by modular Hamiltonian, you mean taking psi naught to be the thermal field double. Is that right?
Exactly. So let's say I take like square a rho to the 1/2 as you taught me as your initial state.
Yeah, and then your H is H left, right? Tensor.
Exactly.
Left, right? In this case, I'm a little bit confused. What is you had this equation, which is H acting on your state K naught. There was this tridiagonal equation.
Yes.
What's the interpretation of that here in this particular state? What does it become?
No, so basically you just take it looks exactly like this. You just take your modular Hamiltonian and all the powers of it acting on this thermal field double, as you call it, And then you apply this Lanczos procedure such that in this basis, in this Krylov basis for this modular Hamiltonian, this modular Hamiltonian becomes tridiagonal with ANs on the diagonal and BNs of the diagonal. And here what I was just saying that you might be interested, what is the meaning of these ANs and BNs in terms of some quantum information like quantities. And the A0s are, for example, entanglement entropies, and B1 is like square root of capacity of entanglement, and there are like higher moments are put into this Lanczos coefficient type combination in this procedure. But basically, the modular Hamiltonian in this Krylov basis will exactly have this Heisenberg form if you finish your Lanczos algorithm.
Thanks so much.
Okay, great. So basically, the story was more tied to operators and basically Heisenberg evolution of the operators. So when we start with some operator O of t that satisfies this evolution equation, so it's I H with O of t. And of course, as you know, we can formally solve this equation by just sandwiching this operator with e to the IHT to the minus IHT. And again, here we can formally expand or rewrite this operator in this following form, again in this series in time, where for all the particular powers of t, we will be getting more and more complicated operators, starting from some initial operator O, then Hamiltonian O with the commutator of the Hamiltonian O with the initial operator, then the nested commutator, and so on. So maybe this sheds some light on what Nima was asking, that basically these operators that we generate in this process by applying, in these times, they become more and more non-local. And then it's actually here, everything is done in the space of operators. And there, it's more natural to talk about the so-called Liouvillean superoperator that acts on everything as basically just taking the commutator of the Hamiltonian with whatever it acts on, such that this operator O of t can be written formally as this e to the I LT acting on the initial operator O. Or in other words, these operators O and tilde here, they are just can be seen as On is just some particular power of the Liouvillean on the initial operator, which is this kind of complicated nested commutator of the Hamiltonian with this initial operator. And again, we have the same problem. So given this subspace O, L of O, and all the powers of the Liouvillean acting on this initial state, we would like to have some basis, construct the basis, orthonormal basis, in which we can actually express this evolution, this unitary evolution in this particular way. And actually, in the story of operators, there's a freedom in doing that. So, because of course, we must pick an inner product in the space of operators, and this is usually done. There's not a unique way of doing this, but actually, in the literature, this has been customarily done with the so-called Whiteman inner product. So, when we take some operator A and B, we denote this curly inner product between them by simply taking their correlator with the thermal. So basically, we take the thermal correlator of this operator A and B with a slight shift of this operator A dagger to beta over 2 on the thermal circle. So an expectation value here, I mean by just a thermal trace with the inverse temperature beta. So I am following this literature on the operator growth. I'm also going to talk about mostly this Whiteman inner product, but actually you could repeat that story for any favorite choice of yours of the Hamiltonian, sorry, of the inner product. And maybe one interesting point, one difference to what I told you just a slide before is that because most of the inner product will involve some kind of trace, when we compute, the trace of the commutator of the Hamiltonian of the operator, this usually by cyclicity, this vanishes. So we can get this way, we can actually get rid of the diagonal pieces AN in the Lanczos algorithm, but otherwise everything works exactly as I specified before, but we don't need to. So I just wanted to point that maybe this story for the states is more general than the story for operators. So let me just summarize basically this idea of Krylov basis. is that we can start with this state, psi of t, with the unitary evolution and expand it in the Krylov basis. And these coefficients, they give you the probabilities. And these probabilities, they capture all the relevant information about the evolution of the state that you might be interested in. Of course, generally, these coefficients may be very complicated, and they, depending on these Lanczos coefficients, ANs and BNs, this equation might be difficult to solve. But in principle, you can go to numerics and try to solve. And then these ANs and BNs, they are captured by this return amplitude S of t, that you can compute the moments and extract them and just solve the equations directly after you know the A's and B's from the return amplitude. On the other hand, for operators, once you have chosen the inner product in the space of the operators, you actually go back to this step of this Krylov basis for state. So you define your state as state corresponding to operator O of t as the application of e to the I Liouvillean t on this initial operator, and then you expand it in this Krylov basis for the operators. I'm keeping this notation here in case you want to check how people what kind of conventions are used in the literature. This table should be very useful. So generally we write this curly phi n of t, this phi n of t, but in the graph of operators, people put this I in front. But basically these coefficients in the space of operators, they are the same probabilities. So their sum goes to 1. And then the Schrödinger equation for this coefficient has 2 terms, because most of the time we can get rid of these ANs. And again, this return amplitude is an overlap between the state at 0 and then state at t. I told you before that I'm choosing slightly different notation. So here people use the star notation with comparing to this one, such that this return amplitude is actually psi 0, curly psi 0 coefficient and not its conjugate, but it's just basically changing t to minus t. Okay, and as you can see, basically most of the story goes very much in parallel, and there are obvious connections. So you can start with some initial state where you take some Heisenberg operator and put it at some time t, and you can study the evolution of that or return amplitude of this state. For example, you can consider a state that reproduces for you the same answer for the return amplitude for the operators for the choice of Whiteman inner product by this particular combination. And most of the other connections are also discussed in our papers if you're interested in direct comparison between one and the other. Okay, so this was just a technical part on the Krylov basis, and now I can finally go to the definition of complexity. So this actually dates back to this work by Parker and collaborators, and basically they noticed that basically because the physics or the growth or the evolution of the state is mapped into a motion, into this discrete Schrödinger equation that describes the motion of the particle on a chain, it's actually natural to look at this chain in the following way, where we have the nodes of the chain as labeled by this amplitudes phi 0, phi 1, phi 2, and so on. And also the transition amplitudes between them given by these Lanczos coefficients B1, B2, B3, B4. So this is, I'm just showing this for the operators, but it can also be done with the choice of ANs. And they notice that the farther in the chain this particle, so the Schrödinger equation, this tells you, describes for you the particle hopping on the chain starting from this initial position at time t equal to 0. And then they pointed that the farther on the chain the particle is, the more complex state in the Krylov basis needs to be employed in order to represent your state or the operator that you are talking about the evolution of. So they proposed that the natural or maybe working definition of complexity could be an average position of this particle on the chain. So in other words, the farther to the right, the average position would tell you at time would tell you what is the distance from the initial point that you started with. And indeed, they proposed that you can just compute this Krylov complexity, or this something that we called spread complexity for states, as basically an expectation value of the position n on the node of the chain with this probabilities Pns. So this will be my working definitions in most of the examples that I will tell you in the moment. There is also a natural way of thinking about this is an expectation value of some operator. So basically, once you have all these Krylov basis vectors, you can just write this operator, and then this Krylov complexity is just an expectation value of this k psi in the state psi of t. Okay, so this is what I will be called the Krylov complexity in what follows. Are there any questions on this, or are you still with me? I'm sorry, the previous part was a bit technical, but I think maybe for people interested in that, applying it, that might also be useful.
Maybe so. If these were states, you have a finite number of states, but these are operators, I guess. So you can have arbitrary number. How is it?
Sorry, I'm not sure if I understood.
Now, if you have, suppose you do this for the states.
Yes.
Then you have a finite number of states. So suppose then the Hamiltonian is finite. So this you can go to the right, but you stop when there are no more states.
Yes.
But if you have operators, you can keep constructing more operators.
So again,
infinite.
that also depends on the initial operator. But let's say if it's some generic operator, then you keep constructing more and more operators. And in principle,
even if the system is finite, no, okay. You also have.
I'll be working with finite dimensional.
So if n is the number of states, you have n squared operators. Or no?
Well, so yeah, I will show you some explicit examples. Maybe this will become clear. If not, please ask me this again, okay?
But this chain is finite ends at some point, so that's maybe the question.
As we'll see, it can go to infinity, but it can also be finite.
Okay.
Can I ask you a question?
Yes.
So this Low-Schmidt coefficient that you said is the absolute value of basically trace of 1 plus rho to the power of 1 plus IT, right? If I take this thermal field double state, but isn't that just exactly the spectral form factor?
Okay. Thank you very much for this question. So I will be talking about it. Yes. Thank you, Nima. Let me just make 2 comments. So I'm not like dumping your question. It will be my next slide. Okay.
Sure.
So let me just make very brief comments. So first, why was the name spread complexity? Well, basically in this paper with Vijay and Javier, we wanted, so of course, just because we call this kind of distance from the origin complexity doesn't really mean that this has anything to do with complexity. So we try to understand basically if there's any kind of natural definition of complexity in the complexity kind of community that could land us on this particular answer. So let me kind of explain a little bit of this inverse engineering here. So basically, the answer to this question is as follows. So let's say you wanted to think about complexity as the way that your initial state spreads in the Hilbert space under this unitary evolution e to the minus iht. How would you define such a quantity? So basically, one proposal that we have was choose a basis, any basis that is appropriately numerated in such a way that this basis vector B0 is your initial state, but any other other vectors in this basis, they don't need to be. They can be any basis vectors that are just going from 0 to blah blah blah, and then. Given such a basis, one can define a cost function or a family of cost functions in the following way. So basically, take your state psi of t at for some finite amount of t and project it on this basis. So this is this probability that you get by projecting this psi of t on this basis vectors psi n square, and then you sum over n with this coefficient cn's. You can write it in this probabilistic way. And then what we argued is that if you choose these coefficients n to be positive so an increasing coefficients in n, so they can go like n or n square or n to some power and so on, as long as they are increasing, then we could show that if you minimize, you can define the complexity by basically the spread of the state in this particular basis minimized over the choice of the basis B. Okay, so if you define your complexity in this way, you can actually show either explicit for finite amount of time, finite. What I mean is like not some finite time around some particular t equal to 0 or t equal to t, and then finite amount around that quantity. Basically, this is some proof using just analysis, or you can use discrete time and basically apply one Hamiltonian here at each step of time, and you can show that the basis that minimizes this cost function is precisely the Krylov basis. So I will not have time to go through this proof here, but you can find it in the first big chunk of our paper.
Well, excuse me. So
yes.
this CP looks very interesting, but it really depends on the choice of basis, right? It depends on two things. One is the choice of basis, the other one is the so-called cost function. So it really depends on two things. So it's, well, for sure, well, you said that you have a beautiful proof, but physically, how can we understand that, these minimum must come from the so-called Krylov basis?
Yeah, so I'm just saying that I'm just choosing this cost CB of t, and this is for a particular basis B, okay? So I'm interested in the spread of the state psi t, and you just tell me, oh, this is my basis in which I can see how it spreads. So just compute this cost function C of B. Your friend tells me, okay, I have a different basis, and in this basis, how does this state spreads? And you compute two different numbers with these choices. Let's say we all agree that CNs in this basis go as n or something like that. So we need to fix this family of cost functions. Okay.
Oh, you first fix the cost function. Say
yes. I fix the cost function.
So in case probably you have considered this particular family, Cn is linearly, is essentially, E is n. So in case you choose another family, so Cn is arbitrary function of n, which may not be linear at all, then could the same conclusion still hold? Say
yes. As long as we agree on some particular CNs. So let's say we choose CNs, and then many people bring different bases with them. What we argue that actually the basis that minimizes this cost function for particular choice of CNs is the Krylov basis.
For any chosen family. So for
any but fixed family.
Okay, thank you. Yeah.
Thanks for this clarifying question. It's very important. So rough argument for discrete time, it's very clear to see. Basically, you start with the initial state, you apply the Hamiltonian, and then you kind of you do evolution, and then you do the perpendicular evolution a little bit, and then you can see that the way you were computing the perpendicular state is just by Gram-Schmidt orthogonalization. So this is like the correct orthonormal state. But if you choose different bases, you can expand that state in your Gram-Schmidt basis plus something else. And as long as the coefficients will be non-decreasing, the CNs, then this cost function will always be bigger than just your Gram-Schmidt basis.
Thank you.
Thanks. Okay, and then, but the point is like once we expand the state in this Krylov basis, that's very also important point, then actually we get this probability distribution PNs that they sum up to 1. And actually this has all the information about the growth of the operator or the growth of, or the spread of the state that you are interested in for any times, okay? And then basically characterizing this evolution can be done, is done in a meaningful way using many tools, as you know, for any probability distribution. So actually here we are just, this K complexity or this notion of the distance is only one quantity, but you can have more tools to really to extract interesting information from this probability distribution. And indeed people computed, for example, information content. So this is this K entropy, which is just the Shannon entropy of this probability distribution Pn. You can compute, if you were wondering why are you choosing n and not n squares and so on, actually there's a nice way to extract information with higher moments of n by computing K variance or K capacity. We also studied, like, for example, exponent of this if you are interested, like if you are arguing, why are you defining the complexity with some particular, in this particular way and not like exponent of something like that, and it's still not clear why any particular definition should be a good one or a bad one. But as long as we have some nice way of characterizing this probability distribution, then we can, any information that allows us to compare these two probability distribution is meaningful, as in probability theory. So I think that's just my message. It's not like so much this K complexity per se, but this probability distribution in this Krylov basis that should be considered as like a primary data that we should be interested in when quantifying this evolution or the growth.
Sorry, just one quick question. So at least the very last point that you made, whether it's exponent or not, is a question of whether you want your quantity to be additive versus multiplicative, right? So which one do you want it? Do you want it to be additive or?
Yeah, I think here for the state, I would probably want it to be additive.
Okay, I see. Also, another thing, so this minimization
Yes.
over B is like sort of, I can think of it as, so you have this sum over n Cn, the overlap of psi t with the Krylov basis, with a u inserted, some arbitrary unitary inserted in the middle, and then you're taking a minimization over that. That looks like a fidelity actually, but maybe we could discuss this later.
Okay. Yeah, I haven't thought about it, but there should be some also more quantum information of expressing this. I agree. Okay, great. So now, how much time do I have, or am I already over time?
No, you have, how much time do you need?
Well, okay, so let me maybe show you like 2 examples and then
10 minutes good, 10 to 15
yeah,
minutes?
then more than enough.
Okay, thanks.
Okay, so Nima, as Nima already pointed out, that we can actually use this construction to go to the states that I started with. Namely, the first example I'll give you is this evolution of the thermophile double. So let's say we take this thermophile double state with the thermal partition function z of beta, and we do some non-trivial time evolution into the minus IHT with some left plus right Hamiltonian or only one left or right. And then the goal would be to expand the state in this Krylov basis and then compute complexity. So as Nima already pointed, in fact, if we would want to do that, then we basically can extract these Lanczos coefficients from the return amplitude, as I was arguing. And in this case, the return amplitude is this log-Schmidt amplitude that appears in the spectral form factor, which is the partition function with shifted to real time. So this is z of beta minus IT over z of beta. And of course, this is non-universal, but can be extracted once we know the partition function. So I will show you 2 examples, namely one trivial kind of sanity check, and then the other one for random matrices that may be more interesting. Okay, so let's
first a question.
Yes,
that's right there. So I guess, but part of the thing that confuses me is that so SFT is this quantity return amplitude that you define, but spectral form factor is the norm of this.
Yes.
Right. And yeah, but in Krylov complexity, you're never dealing with the norm. You're dealing with this complex function and expanding this complex function in powers of del t.
Yes.
Right? Powers of t. All right, I see. There's no way of, is there a direct way of getting some sort of interpretation of the norm, spectral form factor in Krylov terms, or
the norm? Good point. Not that I know. Well, except that this is, of course, just this is some probability amplitude, but okay, like this is kind of like, I'm sure it's not like that's the interpretation you're.
It's sort of like an autocorrelation, right? It's just that's what it is. Okay, thank you.
Okay, so let me just do some simple sanity check. Let's take the thermophile double of 2 harmonic oscillators. So we take this left and right to be just a number operator plus 1/2 with some frequency of omega, and the energies are omega n plus 1/2, and then the thermal partition function is just 1/2 times sine hyperbolic beta omega over 2. okay, so in this case, return amplitude, or this log-Schmidt amplitude I was telling you about, is just you know, this partition function that beta to beta minus IT over 0 over beta, and this is this object. And actually, you can easily compute the moments of this return amplitude and extract directly from these Lanczos coefficients. So you see that ANs, they go as some coefficient gamma n plus 1/2, and BNs, they go linearly as alpha times n, and these are these coefficients gamma and alpha that depend on omega and beta in this particular combination. One thing you should notice is that both of these coefficients, they go linearly in n for large n, but somehow the role of A coefficients is very important. Somehow that, yeah, I will come back to this in few moments, but this is just one comment. And then you can, you know, given these coefficients, you can just plug this into the Schrödinger equation, and you can solve these amplitudes. They are very simple. They have this form, and you can compute this spread or Krylov complexity that actually is periodic like this. So it becomes sine square omega t over 2. So it seems like it gives reasonable answer, and you can plot it now here. So here in this plot in the blue, I'm plotting the norm of this return amplitude. So this is the sine hyperbolic beta omega over 2. Then I'm plotting the spectral form factor, so the absolute value of S of t squared, which is this orange one here. And here at the bottom, in the green one, I'm plotting this Krylov complexity. So you can see that it works in a reasonable way as you would expect it. So this at this time t equal to 0, this return amplitude is just 1. This is by the normalization, and then the Krylov complexity is 0, and then it becomes maximal, where this spectral form factor has a minimum, and then it's actually periodic. It goes periodically like that for 2 harmonic oscillators. Of course, you can actually do something naive and tempting, basically see how the situation changes, where you would consider, for example, inverted harmonic oscillator, and you don't know that this is, you know, as a rule of thumb, you can often do it by just taking omega to I omega in the frequencies, and indeed you can see that in that in that case the return amplitude and the spectral form factor, then they of course also they decay with time. So this is as you would expect for some model that shows not this periodic but more chaotic in quotation marks behavior. But then in this case, if you do this omega to I omega, this Krylov complexity becomes sine hyperbolic, so it actually grows exponentially with this Lyapunov type exponent, which is omega, and you can actually also compute something like a scrambling time, which would be basically 2 over omega log of 2 sine beta over 2. So this is like a rough sanity check behavior that indeed this quantity behave as you would expect in simple models.
Can I ask you a quick question
Yes.
about this example? So I thought this growth of exponential growth of this quantity, or even the growth of bn's with n, linear growth of bn with n, was taken to be some sort of definition of complexity, right? Or sorry, chaotic systems, right?
It's a very important point. Thanks for bringing this out, Nima. So in this spread, when we have just general evolution of states with coefficients ANs and BNs, you can see that in both cases, irrespectively if you have inverted or usual oscillators, this BN, they grow linearly, but also ANs, they grow linearly. And in this case, the complexity is still periodic. You see?
Sorry, I was under the impression that the conjecture was saying that chaotic models will have BNs that grow linearly with N. But this, we're not saying that the simple harmonic oscillator is chaotic, right?
Exactly. And in fact, I think it's the statement. The correct statement is that in chaotic systems, if you only have BNs, which is fine for the growth of operators, you can always set this AN to 0 for the appropriate choice of inner product. Then for the chaotic models, BNs will grow linearly, but the inverse is not true. If the BNs will grow linearly, the model is not necessarily chaotic. So it's a necessary but not sufficient condition.
Maybe I'll ask this at the end, how you set AN to 0, but okay, thank you.
So AN, in the previous case for the operators, you could choose ANs to 0 by simple choice of the inner product. Okay, so
Right? Okay, I didn't notice that. All right.
Lima really basically, well, yeah, this is not the example that we just saw in MO community is well known as a so-called dynamical instability or parametric amplification. So it has nothing to do really with chaos. So
I understand. No, I absolutely understand. There's a conjecture out there that says
exactly
BN
whether this
goes-
conjecture.
BN goes with
I
N.
don't think that conjecture is right.
That's
Yes,
what I'm
yes.
asking. That's precisely what I'm asking.
Yeah. Okay, good. So let me just show you actually even like maybe a statement of this type. We can consider basically we consider a class of models or even a class of states where the evolution in the Krylov space can be represented by such a Hamiltonian. So let's put gamma L0 plus alpha L1 plus L minus 1. This is the representation of a certain of your Hamiltonian in the Krylov basis in this particular form. So I told you that Hamiltonian has to be tridiagonal, and indeed this Hamiltonian is tridiagonal in this particular basis Kn being H and N, and what are the L's and what are the HNs. So here I'm choosing this L0, L1, and L minus 1 to be just generators of SL2R Lie algebra. And I'm choosing the H and N being the standard Lie algebra basis, where I start with some highest weight state and then I act on it with the creation operator, ladder operator L minus 1 to the power N with appropriate normalization. You can check that in this basis, this Hamiltonian is tridiagonal, and you can immediately from the representation theory read of what are ANs and BNs. And of course, ANs are just the diagonal pieces, so they will go as gamma times this coefficient in front of the basis, which is H plus N, and BN, it goes like this alpha coefficient, and then the thing that appears in front of the lowering operator, which is precisely this factor here. So this is the BN and so on. And as long as you can map your evolution of operator or evolution of states into this form, then you can compute you can generically solve the Schrödinger equation and compute the complexity and compute ANs and BNs. And you see that BNs here, they grow for particular highest weight states. They can be shown to grow linearly with N. And also ANs also grow linearly with N in this particular way. And you can show that, by simply applying Becker-Campbell-Hausdorff, these phi-ns, they solve the Schrödinger equation. You can compute Krylov complexity for arbitrary choice of gamma and alpha. So gamma and alpha is this coefficient of L0 and alpha, and this thermophile double evolution of two oscillators was exactly this particular form. If you go to slides and you can read of what are the gamma and alpha in that particular choice. And you can see that for this SL2R evolution, you can see that exponential growth of this complexity will be when gamma is smaller than 2 alpha. But actually when the combination of gamma goes to closer to 2 alpha, or basically where ANs, they go roughly like 2 times alpha times N, and Bn goes as N, so basically there's this particular combination, you can see that this sine hyperbolic becomes quadratic. So there is a slower growth in these particular models. Actually, you can even go for the harmonic oscillator, the usual one, you can see that this combination becomes negative, so that becomes imaginary, and this sine hyperbolic just becomes sine. So you have these free regimes of the parameters where you can check that how this SL2R evolution can work. And in particular, actually, in these cases, you can check that this Krylov complexity is roughly the variation in the expectation value of this L0 generator. So if you compute L0 in the stated psi of t and subtract L0 expectation value of L0 at the initial state, this will be exactly this value. This is just an observation. Okay, so I hope this clarifies a little bit. And then maybe to more non-trivial applications beyond the harmonic oscillator, we can do the same story, but for some random matrices. So let's choose the evolution of a thermophile double with some n by n Hermitian, either Gaussian or symplectic or orthogonal random Hamiltonian. We can again start with this random Hamiltonian with some random numbers, put it in this Heisenberg form, exponentiate it, and apply it into the thermophile double state. The trick is that when you put it into this Heisenberg form, you have to be a bit careful. So in this Python and Mathematica packages, they always do it with respect to some vector, initial vector that has this form 1, 0, 0, 0. So you need to make sure that you first rotate your thermophile double state into this form and then exponentiate and apply, and that immediately gives you all these coefficients phi n's of t. It's a bit technical, but it's pretty straightforward, and you can go like that up to very large numbers. So let me just show you the final result. Well, you can compute this complexity of the thermophile double state for initial time, and you can check that indeed it grows quadratically. But then it actually has 4 particular regimes of the evolution. So after this initial time, it grows with this ramp. That's what we call the ramp here in this picture. Then it reaches the peak. Then it follows, this peak is followed by some slope, and then it reaches a plateau at a very late times. This is this peak of spread complexity divided, Krylov complexity divided by number n, plotted for various temperatures, inverse temperatures beta, and then as a function of time, again, normalized by this n, and we studied it with n from 1024 to 4096. Let me just compare this for the spectral form factor that we usually plot as the log of the spectral form factor as a function of log of t, and it also has these 4 slopes, deep, ramp, and plateau. Basically, so there are many interesting parts in this plot. Here we plotted it, you can see kind of self-averaging. So we plotted this for all these particular values of n for fixed temperatures, and you see that they base their difference and some small fluctuations, they're basically very close to each other. So we did not do any averaging here, whereas here we did averaging. One nice way to actually explain these 4 regimes in this complexity can be done by plotting this probability distribution, and this is done here as a function of n. This is on horizontal for different values of time. So you can see that at t equal to 0, as we did by construction, this amplitude has to be picked at the initial state, and you see this is exactly this sharp peak where we start from. This is this thermophile double. But then this probability tells us like how this, on which states in this chain, that in this kind of, this Krylov chain is my state at time t supported. And you see that actually as time grows, this state evolves kind of ballistically in this Krylov basis up to this peak, where it reaches the most, because we are working with large n, but still finite dimensional Hilbert space, then there will be some most complicated state in the Krylov basis that we're going to read, and that's exactly where we reach this state up to some peak here, actually at time 3000. And after that time, once we reach this most complicated Krylov basis vector, this evolution in the Krylov space starts to spread or kind of thermalize equally on all the basis vectors, and that's actually this part where it starts going back from this most complicated one. It's this slope part, and finally, after some time, once all the states are equally, supported, let's say, or occupied, this is where we reach this plateau. So that's why we have these 4 regions nicely interpreted in terms of this probability. There's also another interesting observation that you can do. Maybe here you see that there are always, on this plot, there's always like 2 curves. One is the darker one that has this peak and slope and plateau and ramp. And there's a lighter blue, for example, that only has this ramp and plateau, and similar for other temperatures. So what's the difference between them? Actually, we tested what kind of physics can this spread complexity be sensitive to. And in these light ones, we got rid of the correlation between eigenvalues of the matrix, of the random matrix, by simply choosing the eigenvalues of this Hamiltonian from the Wigner semicircle. This is known that as a procedure of getting rid of the eigenvalues between, correlations between eigenvalues of the random matrices. And actually, you can see this in that procedure. If we repeat the spread complexity for this without these correlations, we don't get a peak and a slope. If we do the same for the spectral form factor, this is also the lighter curve. After the averaging, we have a slope, but then we don't go to the dip and the ramp. Immediately after the slope, we end up with the plateau. So this light curve here, it's actually the lighter curves here. Okay. So yeah, I had other parts about the more like older operator growth, but I think I have went through over time already by a far. So let me just conclude. I was trying to argue that we have a new definition or some framework for complexity that uses this Krylov basis, and it's kind of nice because it can put into one framework both this complexity of states and growth and complexity of operators. And this definition is nice and algorithmic in a sense that for any operator or any initial state and the Hamiltonian, we can do this expansion, we can construct the Krylov basis and really compute this quantity. For random matrices, it has these 4 regimes. It has ramp, peak, slope, and plateau, similarly to the spectral form factor. I was trying to argue that there's also a nice symmetry approach to this by simply studying what kind of algebra, or say, usually in the old literature, it was called the spectrum generating algebra, can be applied to represent this Liouvillean or Hamiltonian in the Krylov basis. And we applied this nicely for the SYK or 2D CFTs that I did not have much time to talk about it, but you can find it in our paper. But of course, you know, there are like bigger and deeper questions when we want to apply it more to holography and and you know, to many body systems. And basically for holography, the main question is why Krylov basis? We usually tend to think about meaningful things as basis independent, but in some sense, we have to agree that once we probe this story beyond entanglement and this complexity, we want to really have a good understanding of the relation between bulk Hilbert space and the boundary Hilbert space. And in particular, we would like to understand what some choice of the basis in the bulk correspond to in the boundary and vice versa. So there has been some progress on this by Henry Lin, where he looked a little bit at the relation in double SYK model and the chord diagrams. And he was arguing that actually there's some nice role played by Krylov complexity there, but I think this was just the first paper, and probably something more is coming on that. And also maybe for the future, we would like to understand whether this spread and complexity is something universal and also useful for quantum information or quantum computation. You already had many great questions like what is the physics between these coefficients or overlaps? Can we understand it more from quantum info or quantum computation? I think this is pretty much open. And of course, also questions like general behavior for holographic CFTs. Let's say that we only assume some large end and the gap and maybe a few more things. Then what is the generic behavior for such a model? I think some partial answers are known, but still it's to be determined. And finally, yeah, like complexity, a relation between complexity and near horizon geometries for this operator growth. That's still something interesting I would like to understand better. And finally, precise connections with holography, whether there is a room to find the holographic dual, or is this actually the type of complexity that we might be interested in any discussions or not? This is still an open question. But at least I hope I convince you that we have some framework that for something that might be a nice notion of complexity in many body systems and even holography, whether this is something that we want for holographic complexities now, future will show. So thank you very much. Stay tuned and join the fun.
Thank you so much, Pawel, for the beautiful talk. We have a lot of questions, but are there more questions for Pawel? I have a bunch of questions actually. Let me start by one and then we'll wait for other people to ask more questions. So this, you said that the early evolution of complexity is ballistic motion of this wave packet towards larger n, right?
Yes,
And then you said that it saturates, it reaches a maximum complexity. Is that some sort of artifact of the finite dimensionality of the Hilbert space?
precisely. So here it just reaches this maximal state. So basically the dimension of the Krylov basis is always bounded by the dimension of the Hilbert space.
So, but does it, so when you say ballistic, do you mean it moves exponentially fast or is it linear?
Oh no, sorry. Yeah, when I mean it just moves like, yeah, maybe ballistic was not a good. So
the wave packet moves coherently, but it speeds up. It goes exponentially fast.
Yeah. So no, it moves kind of coherently to the right. But whether this is a well, it is.
I guess I'm asking what's the time scale of the peak in terms of the entropy?
Yes. So peak was like exponentially in entropy.
E2 paravax. I see.
Yes.
And then, so then you also see this comment that you made about random matrices getting rid of the eigenvalues.
Yes.
So that sounds like a tallest time, right? So where those two plots meet, right? The dark blue and the light blue. Is that tallest time? Do you see how it scales with entropy and stuff and beta?
Yeah, that's a good question. Actually, we have not looked into that.
Am I interpreting this correctly? That where they meet is the tallest time?
I think that's how people defined it, right? For
the onset of the random matrix model.
Exactly.
I've been curious about like how much larger is this compared to E2 paravax, and now I saw like some sort of separation. I was curious about this.
Yeah, actually, that's a great question. Yeah, to be honest, we have not looked into that, but
I have one more question, but I'll wait if other people have questions.
That's a good point.
Any last questions before I have a little more?
There's something in the chat.
No,
no, I just need to go. Oh, sorry, I need to pick up my kid. Thank you very much. Okay, this is
thank you so much. Yeah. So just very quickly. So you mentioned this SL2R model. So SL2R, my first reaction was that you probably have something like a CFT in mind, a 2D CFT in mind. But then I realized that you don't really need a 2D CFT. You could be talking about squeeze coherent states, for instance.
Exactly.
Right? There's an SL2R there, and this could be a quantum mechanical system, just a simple harmonic oscillator with squeeze coherent states.
Yes. So you see, the point is like, that's precisely what. So for example, in 2D CFT, like in SYK, the reason why people also like we saw this in the SYK model is that people choose this return amplitude to be roughly a 2-point function in CFT for this growth of operators. And that 2-point function, again, it's fixed by SL2R. Okay. So that's one case, basically, that you get this cosine hyperbolic here in the point, and your comment about the squeezed state was exactly there. So basically, when we think about the evolution with this Hamiltonian, that is like L1 plus L minus 1, that's exactly the SU1, 1 state from quantum optics, that you can represent this growth of the operator by precisely that state if you just tweak these parameters of the state by your physical time in an appropriate way. Okay.
Sorry, so your physical time makes the state more squeezed, is that right?
Yeah, precisely. So this rho of the state becomes your physical time in this quantum optics interpretation.
And then in the t going to very large limit, the state becomes basically classical because you're extreme squeezing, right?
Yes, but you see that basically in this representation, this cosine hyperbolic that was your phi 0, it appears exactly in this denominator, and this is your return amplitude.
Sorry, I didn't get the point.
Oh, sorry. So basically, your return amplitude, that was this 2-point function in the
Right.
thermal state.
Oh, yes,
That is this phi 0 of t, and that's this becomes 1, this becomes 1, and that's this cosine hyperbolic to the power eta alpha t in SYK.
But your point was that the return amplitude is fixed by the SL2R.
Exactly. So in this case, like in 2D CFTs, in SYK at large Q, and in many other models, like this return amplitude, also in these two oscillators, the return amplitude is fixed by SL2R, and then it kind of works like that.
Thank you so much. All right, any last questions for Pawel? We kept him for a very long time, but are there any last questions? If not, let's thank Pawel again for the beautiful talk.
Thanks a lot for attention, and
Thanks
sorry
so much.
for going over
I
time.
really enjoyed this talk. This was wonderful. Sorry for being a few minutes late at the
Are
beginning.
you by any chance coming to the Eat from Qubit meeting?
Oh, it's from Qubit. Yes, I'll be going to it from Qubit.
Okay, then see you soon
I'll
in
see
New
you.
York.
All right.
Thank you very much for
Thanks.
questions. Take care.
Bye, thank you.
Bye.
Bye.